In this video, I'm going to cover several different things, but what we're going to begin with is what is called the rational root theorem. To begin with, what I have here is a higher degree polynomial set equal to 0. Okay, 2x to the fourth power with all these other terms that follow behind it. Next to that, I actually have the same polynomial, but in factored form. Okay, still set equal to 0. So if you were asked to solve this, to figure out what values of x make it equal 0, solving from standard form is pretty difficult. And what you've been taught in the past with quadratics, and maybe even cubic functions, is factor. If you factor this apart, you can easily identify your roots, also called zeros. Okay, so in the factored form, what I can learn here is that any value that when plugged in for x makes that respective set of parentheses equal to 0 would represent a root. Okay, so for this one, it would be the opposite of 5 divided by 2, so you get negative 5/2. For this, it would be negative 1, and for this, it would be 3. And those are your roots. And as a side note, you'll hear about this later in a different video. This is what we call a double root. Okay, it's a double root because that factor counts twice. That again will be addressed in a different lesson. All right, so as I said before, by now you know that factored form is a more convenient way to solve polynomials. Yet, if you have a higher degree polynomial and it's in standard form, it might be too difficult to actually break it down into its factors. Okay, the example that we have above, it is near impossible to figure out that the factors to this would be these. It is near impossible to do that. Okay, so we have something that's called the rational root theorem, a way to start identifying what would be potential roots. Now, in some cases, it creates a very large list of numbers. However, if the polynomial does have rational roots, that means that they could be fractions or whole numbers, but they wouldn't be square roots or imaginary numbers. Okay, the list would still contain them. So the list might be a little bit long, but somewhere in there, if there are rational roots, they will be in the list. Okay, so how do you create this list of potential rational roots? We're going to let p be the constant. Okay, so I'm thinking about standard form now. So p as my constant is going to be the 15. Okay, technically it's negative 15, but you're going to notice in a second we're going to consider all possibilities of positives or negatives. So you can really just look at the 15. Okay, so p is going to be 15. Q is going to be the leading coefficient, which is the 2. And we're not going to pay attention to any of the other numbers. You have a 15 and you have a 2. We're going to list all the possible factors of p across the top here. Okay? So all the possible factors of 15 would include 1, 3, 5, and 15. Those are all the factors that go into 15. You get the trivial ones. You got 1 and 15. Then you've got factors that are, a little more unique. You got the 3 and the 5. But those are all of them. The factors that go in 2 would be a 1 and a 2. And what we're going to look at are combinations of numbers in the top with numbers in the bottom, and those could all potentially be the rational roots. One value you can actually just kind of remove on its own. You don't really need the 1. But what it does represent, because this is important, what it does represent is that 1, 3, 5, and 15 are all possible roots. All possible. It doesn't mean that they are. They're all possible roots. In fact, the positive or negative of all of those would be possible roots. And one of them, negative 1, is there. Negative 1. That would have been one of your possible ones. Okay, now the full list that we got that we would take from this would include, it's going to be lengthy here, you're going to have 1, you're going to have 3, you're going to have 5, you're going to have 15, and all of those divided by 1. In addition to that, you're going to have all of these divided by 2. So you're going to have a 1/2, you're going to have a 3/2, you're going to have 5/2, 15/2. So there's 16 potential, right? I got 8 here, but they can be positive or they can be negative. So the list is a little bit long. It is. But if rational roots do exist here, they're in that list. And let's identify them. Negative 1 would be right there. Just take the negative of it. Now, that doesn't mean that positive 1 couldn't be 1 as well. It just happens to be that it's going to be negative 1 here. Negative 5/2. Here it is. just as a negative, and 3. They exist in there. Somewhere in my list of 16, positive and negative, all of those roots, which were rational, did exist. All right, so let's look at an example of this. Suppose that we have this polynomial here, and it were set equal to 0. So we're looking for the roots that go along with it. Okay, what we would need to do for a rational root theorem is to figure out all the factors that go in 6 and all the factors that go into 2. So for 6, that would include 1, 2, 3, and 6. For the 2, that would be a 1 and a 2, which you can just write the 2. Overall, it gives us a list that looks like this. And they're all going to be positive or negative. Okay, it's going to be positive or negative. You can have a 1, a 2, a 3, a 6, if those are each divided by 1. And you can also have those divided by 2, which would be 1/2. 2 divided by 2 is actually 1, so you don't need to write that one down. We've already got it. You got 3 divided by 2. 6 divided by 2 is actually 3, so you don't need to write that one. So we have a total of 12. Okay, and then what you do with them is you just guess. You just guess and see if one of them might be right. And you can test that guess using synthetic substitution, okay? If we were to plug these in to that polynomial and the result come back as a 0, that means that it was a root. Okay, so what I'm going to do is show you an example of one that doesn't work to start with, which is going to be the 2. So I'm going to put 2 in the little box, list the coefficients. We don't skip over any degrees here, okay, so no fillers. Okay, and then we're going to run the course of this. We'll drop down the 2. 2 times 2 is 4. Okay, add it together, you get 3. 3 times 2 is going to give you 6. Okay, -7 plus 6 is going to give you -1. -1 times 2 is -2, which results in 4. We need it to be a 0 for this to be a root. Okay, so here's an example that does work. You could use 1. Okay, 2 times 1 is 2. With the -1 is 1. That'll give you 1. -7 and 1 is -6. Times 1 is -6. Results in a 0. So, +1. +1 is going to be a root. It is going to be a root. Okay, now how do we get the rest? Do we really just guess and check? Do we really just guess and check a total of 12 times? No, because this is a root. Since this is a root, then we know that there's a factor of x minus 1. There's going to be a factor of x minus 1. It's going to look the opposite because this is the root. And if we had divided this by x minus 1, we would use the opposite number, divide it, and this is what you would get back as your quotient. So that actually represents 2x squared plus x minus 6. We have that as a factor. The rest of it is a quadratic that we can probably factor by parts. All right, so let's go ahead and factor that. We got 2x squared plus x minus 6. Because I have that coefficient of a 2, I'm going to use factoring by parts. I'm going to think of 2 numbers that multiply to give me the same product as this, which would be -12. 2 numbers that multiply to give me -12, but group together to give me +1. Those numbers are going to be 4x, well, it's going to be a 4 and a -3, but we're going to attach x's to them. All right, and then we factor by parts. The GCF here is going to be 2x, leaves you with x plus 2. All right, so then the other one needs to have an x plus 2 as well. And we can factor out a -3 to make that happen. So overall, let's put it all together here. The original polynomial in complete factored form is going to include this factor, and it's going to include x plus 2, and it's going to include 2x minus 3. So if we were to set that equal to 0, the roots would be 1, would be negative 2, and positive 3 over 2, which were all part of the list that we originally saw. In addition to the rational root theorem, what I wanted to do was address roots in general, whether those roots be real numbers, irrational numbers, or even imaginary numbers. In the complex number system, which would be the real and imaginary number system, if p of x is a polynomial function of degree n, then the equation has exactly n roots. Those roots might not be integers, they might not be rational numbers, they could be irrational, or they could even be imaginary numbers. Okay, but you will have n roots if you have a degree n polynomial. For example 1, we're not actually going to factor this out, but because it is a degree 4 polynomial, it will, in some sense, have 4 roots. They may be integers, or rationals, or irrationals, or even imaginary numbers, but it will have 4 roots. Complex conjugate theorems. If p of x is a polynomial with real coefficients and a plus bi, that would be a complex number, is a root for p of x equals 0, then a minus bi, the conjugate to a plus bi, is also a root. Example 2, if 1 plus I times the square root of 2 is a root to this polynomial, then the conjugate will be another root, and that conjugate would be 1 minus I times the square root of 2. Again, if p of x is a polynomial with real coefficients and a plus the square root of b is a root for p of x equals 0, then the conjugate, a minus the square root of b, is also a root. Example 3, if 3 over 2 minus square root 5 over 2 is a root for this polynomial, then the conjugate would also be a root, which would be 3 over 2 plus square root 5 over 2. Example 4, find a quadratic equation with root 2 plus 3i. All right, if we got that complex root, then we're also going to have the conjugate of that complex root. So the roots that we have here are going to be this and the conjugate, which will be 2 minus 3i. Those will be our roots. Okay, and if we're attempting to build a quadratic, what we would usually do is take those roots and plug them into the factored form of the quadratic, which would look like this. You would have x, then you would subtract whatever that root is. Okay, so this is going to look a little bit messy. Oh, second set of parentheses there. Okay, you would take that root and subtract it from the x. You would also do the same thing with the other one. All right, and then we can distribute that negative in so that we get x minus 2 minus 3i. We also get x minus 2 plus 3i. All right, so then the question is, how do we take this and put it into a standard form? Okay, because that really doesn't look that nice, and we can probably present this in standard form much better. Okay, now, since we got a lot of terms here, what we're going to do instead of a lot of distribution is to refer back to the sum and product rule that we recognize from quadratics. Usually to identify these numbers, what would go into these parentheses, what we would do is look for a couple of values that multiply to give you the constant and add together to give you this coefficient. So what we're going to do is just go ahead and add these together to create that coefficient and also multiply these to get that product. Okay, so adding them together, we're just going to take negative 2, negative 3i, negative 2, and positive 3i. Okay, we're just taking this part here and that part. When we add those together, we should get our sum, which is going to be that coefficient. Okay, the negative 3i and the positive 3i, those are going to cancel with each other. They cancel out, which is kind of nice because it removes the imaginary part. The result that we get is going to be negative 4. All right, so the product is going to be negative 2 minus 3i times negative 2 plus 3i. Okay, and as we multiply, you get a positive 4. You also get a negative 6i. You get a positive 6i. Those will cancel. Okay, and then a little bit more complicated here. You're going to get a negative. You're going to get a 9. You're also going to get an I squared. Okay, so these cancel. We can take those out. Here, I to the second power is going to become a negative 1, which is going to cancel that negative. We get 4 plus 9, which is 13. So all together, we can take these numbers and plug them into these spots. We're going to get an equation that would be y equals x squared minus 4x plus 13. Example 5, find a cubic equation with integral coefficients, that just means integer coefficients, that has the roots I square root 2 and 5. It has the roots I square root 2 and 5. Okay, that is only 2 roots that are being provided for us, right? We've got the 5, we've got the I square root 2. But according to one of our complex conjugate theorems, we should have the conjugate of any complex number. So we're going to think of this one as 0 plus I root 2. And the conjugate to that would be 0 minus I root 2. So our third root is negative I root 2. So given these 3 roots, we can actually build the cubic equation in factored form. We'd have x plus 5. Actually, they will be opposites. We will have x minus 5. We're going to have x minus I root 2 and x plus I root 2. And if we multiply all this together, we should see in standard form that we will have integer coefficients. Okay, where I'm going to start is going to be here, because these are actually the difference of squares, which means that you don't need to distribute everything. You can actually just look at it as the difference of squares. Okay, so you're going to have an x times x, which will give you x squared. We could multiply the x to this value, multiply this value to the x, but being that we have conjugates, they're all going to cancel out. So we're just going to jump to multiplying these 2 parts. You're going to have negative times positive, which is negative. You're going to have the square root of 2 times the square root of 2, which is 2. You also get I times I, which is I squared. That I squared will become a negative 1, making this positive. And we still have this factor. And from here, we can do our regular distribution. We've got x times x squared. We've got x times 2. Negative 5 times x squared. And negative 5 times 2. And if we slightly reorganize this, we can get it in standard form. We've got y equals x cubed. We're going to move that forward. And that's it.
Wait, what?